Today we start a series of videos on chemical kinetics, which is the study of the factors that determine how quickly reactions occur. Some reactions occur slowly, some occur quickly, and up to this point we haven't talked much about how fast they go, just what happens during chemical reactions. If you want to study chemical kinetics, you need some way to talk about how fast reactions occur. And so a real basic here, before we get started, is to define rate of reaction. So very generally, we could say that the rate of reaction is the speed at which a reaction will occur. In terms of reactants, this means how rapidly are reactants being used up. In terms of products, it means how rapidly are products being formed. And another thing that rate of reaction can do is it can give us a clue about the mechanism of a reaction. We write down reactions on paper and assume that they will happen just exactly the way they're written. But a lot of reactions, it turns out, don't exactly happen the way we write them down. There could be a series of steps called a mechanism. And the rate of reaction can tell us what kind of mechanism might actually be at play when a reaction is taking place. Let's take a look at some factors that will influence how fast reactions go. One of them is just differences in reactivities of substances. They'll cause differences in rate. Some things just react better than others or faster than others. For example, if you cut a piece of sodium and expose it to air, within seconds it's oxidized and the surface is no longer sodium but sodium oxide. Iron will do the same thing. If you shine up a piece of iron so that it's just bare iron and leave it exposed to air, after a while it will oxidize and you'll have iron oxide or rust. But it takes a lot longer, more than just a few seconds. We can also see a difference here in the reactivity of two different metals with the same acid. Here I've got 6 molar hydrochloric acid in 2 different beakers. Into one of them I'm going to put a piece of copper wire, and into the other one I'm going to put a piece of magnesium ribbon. So there goes the copper wire, and here goes the piece of magnesium. You can see immediately, as soon as I drop in the magnesium, there's a violent reaction. I'm producing hydrogen gas and magnesium chloride. But on the other beaker, there doesn't seem to be anything happening. We take a closer look, we can see in the bottom of the beaker with magnesium, there's nothing visible. It looks like the magnesium has all reacted. However, the copper wire looks completely unaffected. So differences in reactivities are one of the factors that can cause differences in rate. Another factor is the ability of the reactants to meet each other. Later on we'll learn something called collision theory, but the guts of collision theory really is just saying that in order for two reactants to react with each other, they have to come in physical contact with one another. Well, the more likely it is that the reactants can meet, then the faster the reaction is likely to be. So we can divide reactions into 2 types of reactions. One is called homogeneous reactions. And homogeneous reactions are reactions where everything is in the same phase. Heterogeneous reactions are the other type, and that is where the reactants are in 2 different phases, like one is a liquid and one is a gas. If you have 2 gases mixed together, well, the reaction is going to go more rapidly than if they have to enter a different phase before reaction can occur. An example, gasoline vapor versus liquid gasoline. You may not know this, but liquid gasoline doesn't react very fast. In fact, you can barely light it without some vapor. Here you're seeing a fire pit, and there's some snow in the bottom. It's very cold out, and there's an aluminum pie plate. In the aluminum pie plate is some gasoline that's been poured in there. Now, it's about 30 below, and so the vapor pressure of gasoline above the pie plate is very low. I'm going to attempt to light a match and see if we can get this to start. Throw the burning match into the pie plate and it just goes out. Liquid gasoline extinguishes the flame, actually smothers it. Try again. Comes another match. It also goes out. Now those 2 matches probably have vaporized enough gas now with their heat that I can get it lit, and there it goes. The 3rd match lights it. Vapor gasoline burns. Liquid gasoline doesn't. Homogeneous versus heterogeneous. So gasoline vapor reacts very rapidly, but gasoline liquid can actually put matches out. Heterogeneous reactions are faster if the contact space or the contact surface between the 2 reactants is bigger. Generally, this happens if you have smaller particle sizes. An example of this is grain kernels, which will light on fire and burn slowly, compared with grain dust. Every few years, you'll hear a news story about a dust explosion at a grain elevator. The small, fine particles of grain that make up dust will burn at a much more rapid rate, something that approaches an explosion. Watch this demonstration with something called lycopodium powder. Here we're seeing a video from this guy named Steve Spangler, and he's got some lycopodium powder here. These are tiny spores, so it's very small particles that he can squeeze out into the air. And now he puts a little bit of it on the table here, and he's going to attempt to light it as a bulk, as a solid, and he can't get it to light. Now he's going to take the same stuff and squeeze it into a candle as a powder. Watch what happens. As a powder, it reacts violently, but as a solid with large particle size, it wouldn't. Now he's got this other contraption. Check this out. Huge explosion from dust. Here's why that works. If you take a look at the surface area available for two different versions of the same amount of substance, you can see the contact area will be much larger with smaller particle sizes. Imagine that you have a cube of some material, some reactant, that has 1 centimeter edges. The total volume of material here is 1 cubic centimeter. What's the total surface area? Well, on each face you're going to have 1 square centimeter, because we have 1 centimeter edges. And there are 6 faces, so that means the total surface area for contact between reactants is going to be 6 square centimeters. Now, if we have 1,000,000 little cubes that each have 1/100th of a centimeter edges, the story is completely different. The volume is going to be 0.01 centimeters cubed, and that turns out to be 1/1,000,000th of a cubic centimeter. But if I have 1,000,000 of them, that means I have a cubic centimeter, just like the large cube. Now let's look at the difference in surface area. Each face of one of these little cubes is going to be 0.01 centimeters by 0.01 centimeters. So that's 1 times 10 to the minus 4th square centimeters per face. And there's 6 faces, just like there is for the big cube. So this means 6 times 10 to the negative 4th square centimeters per cube. Now let's multiply that by the number of cubes. 6 times 10 to the minus 4th square centimeters per cube times 1,000,000 cubes. What we get is 600 square centimeters. So with the small particle sizes, the same amount of material can give us 100 times more surface area for contact with the other reactant. So the reaction goes way faster. Another thing that influences reaction rate is how concentrated are your reactants. Because higher concentration in a solution or in air means that there are just more particles per unit space to contact each other, well, that means it's going to result in a faster reaction. An example of that would be a wood splint. A classic test that chemists use to determine if they've created oxygen is to take a glowing splint, which in air, which is 20% oxygen, will just glow, and stick that into the gas in question. If it bursts into flame, that higher concentration of oxygen caused that to happen, and so probably you've created pure oxygen. Another example would be if you compare a low concentration and a high concentration of hydrochloric acid with the same reactant, like this. Here I have 2 beakers that both contain hydrochloric acid, and I'm going to put zinc into them. On the left I've got 0.1 molar hydrochloric acid, and on the right I have 12 molar. As soon as I drop the zinc pellets in, you can see the 12 molar HCl is reacting violently with the zinc, but it doesn't seem like very much is happening with the 1 molar hydrochloric acid in the zinc. If I take a closer look, looking in the 0.1 molar hydrochloric acid, I can still see that the zinc piece is completely intact. When I look in the 12 molar beaker, there's no zinc left, just a little dirt that was probably stuck to the zinc. It's completely reacted, much more quickly. Another factor that influences reaction rate is temperature. Almost all reactions run faster at a higher temperature. And I guess that makes sense if you think about it, because the particles are jiggling around more rapidly. It's just more likely that they're going to contact one another at higher temperatures. An example of this is the insect activity on a cool evening in the summer. Insects are cold-blooded creatures. They're not like us. They can't regulate their temperature and keep it at the same temp all the time. So when it gets cold out, the chemical processes that make an insect function start to slow down. And you might have noticed this in the summertime. You can have a day when the mosquitoes are awful in the early evening, and then it starts to get cool after dark, and it gets down to about 55 degrees or between 55 and 60, and there are no bugs anymore. And it's not because the bugs went home. They're just not moving because their chemical processes are just happening very slowly. Another place you can see this is in light sticks. This demonstration will show you the effective temperature on reaction rate. Here's a video of a guy with some light sticks. He's got 3 light sticks and he has 3 beakers of water. One of the beakers is hot, very high temperature water, and one is very low temperature water. He started all the light sticks and you can see that they're glowing with about the same intensity right now. Now he's going to put them in his water baths. So he puts one in room temperature, cold, and hot. And a little bit of time elapses. And at this point you can clearly see that the cold temperature and the room temperature are not glowing nearly as brightly as the one that's at high temperature. You'd expect that because higher temperatures produce faster reactions. Faster reaction means more photons, and that means brighter light. One more thing that influences reaction rates generally is something called a catalyst. A catalyst is a substance that increases the rate of a chemical reaction without experiencing a net change itself during the process that it's catalyzing. An example of this would be H2O2, hydrogen peroxide decomposition. If I take some hydrogen peroxide, H2O2, and allow it to decompose, it'll naturally turn into water and oxygen gas. But this process is very slow. You may notice at home in your medicine cabinet, if you've got a bottle of hydrogen peroxide, look at the lid. It's got a tiny pinhole in it, and that hole is to let oxygen out so it doesn't explode inside your medicine cabinet. But the process is so slow that you almost really don't need that little hole. Even when the concentration of H2O2 is pretty high, the process is quite slow. However, there's a catalyst that you can add that'll make the reaction go much more rapidly. In fact, anything that contains the iodide ion will do this catalysis. And so you could use Ki or NaI solutions, and it'll make the reaction go much more rapidly. Watch. Here we have 2 chemists that are about to decompose some hydrogen peroxide into oxygen and water. And this is going to happen in soap, so you should see bubbles. Now, they've got the stuff in some graduate cylinders right now, but nothing is happening. Watch what happens when they add a catalyst. The reaction goes much faster with the presence of a catalyst. That hydrogen peroxide basically would have stayed there all day and nothing would have happened, maybe even for months. But with a catalyst, it's much quicker. So let's define reaction rate. Reaction rate really is the change in concentration divided by the change in time. You might recognize this from physics or from a math class, that changes of anything with respect to time is a rate. So like speed, for example, is change in position with respect to time. Well, rate of reaction is measured as change in concentration divided by change in time. The reaction rates for a chemical reaction are stoichiometrically related. Just like the quantities of substance involved are stoichiometrically related, they have to be tied together in terms of reaction rate as well. The reaction rate for a reactant is negative because it's going down. Its concentration is decreasing. The reaction rate for a product is considered positive because its concentration is going up as more and more gets formed. So if you have this reaction, for example, which is a combustion of butane, you might ask yourself, if the rate of consumption of C4H10 is minus 0.20 moles per liter per second, what's the reaction rate of CO2? And here's how you can solve this. It's just like a stoichiometry problem. If I know that my rate is negative 0.20 moles of C4H10 per liter per second, and I know that the mole ratio is 2 moles of C4H10 for every 8 moles of CO2, the only thing I have to do is modify for the fact that one's a reactant and one's a product. So it's a negative 2 for C4H10 and a positive 8 for CO2 because it's a product. When I multiply this out, I get 0.80 moles of CO2 are being produced per liter second. One place where this is helpful is if you have a reaction that's easy to track one of the species but not so easy to track the other species, you can measure the reaction rate of one of the reactants or products and then figure the rest of them out from there using stoichiometry. An example would be this. If I'm decomposing HI, I will get 2 products, H2 and I2. It's very difficult to track the loss of HI because it's colorless. It's very difficult to track the production of hydrogen because it's also colorless. But iodine is purple. And so if I have something that can measure purpleness, and there are tools that can do that, that's what I would want to track. And then I'd know what's going on with the other species in the reaction as well.